Okay, so we can get started then. Thank you all for joining us. So today we're going to continue on with our series of outcome talks from the eScience Winter Incubator. And I'll introduce Sarah Stone in a minute, who will talk a little bit more about that program and then introduce the speaker. But just a reminder of our etiquette. So keep yourself muted unless you're speaking. And at the end, when we're ready for questions, we will use the hands up icon that you can find underneath the participants button on your bottom of your Zoom screen. And we'll just go through, when you hit that, it'll pop up to our list and we'll go through and call on you individually. So Sarah, you ready to get going?
Yep, ready to
Sarah
get
Stone.
Yeah, thanks, Dave. We're having 2 additional talks that come from the eScience Winter Incubator program. Just as a reminder, if you haven't heard about this program, this is a program we run in winter quarter where a researcher is paired with a data scientist to work on a tractable data science challenge in their research. And today we're going to hear 2 talks, and we're starting out with a talk by Ariane Ducellier. And she very kindly, some constraints that we had, has recorded her talk, and I will be advancing her slides while playing a recording of her talk. And she will try to come in for the question and answer session at the end of her talk to address your questions. So hopefully that'll work out. And again, many thanks to her for making this work. Ariane is an Earth and Space Sciences grad student, and she worked with data scientist Scott Henderson from the eScience Institute, who is also a research scientist in Earth and Space Sciences. So without further ado, I will get going. The sound on her recording may be a bit quiet, so you may find that you need to turn up the sound a bit during her talk. And please holler if something isn't working right. Okay, here we go. Thanks, everybody.
1. Hi, my name is Ariane Ducellier. I am a PhD student in Earth and Space Science, and I study seismology. And today I'm going to present my incubator project on daily monitoring of low-frequency earthquake activity. Slide 2. Low-frequency earthquakes are a particular kind of earthquake with magnitude about 1 and which frequency content is about 1 to 10 Hz, which is lower than what we see for a regular earthquake of the same magnitude, for which the frequency content can be up to 20 Hz. The source of the low-frequency earthquake is located on the plate boundary between a continental crust and the subducting oceanic crust. Slide 3. One particularity of low-frequency earthquake is they are grouped into families of earthquake. That is, all the low-frequency earthquake from a given family originate from the same patch on the plate interface. So on this map of Northern California, we can see that all the black dots are the source of low-frequency earthquake family, and all the low-frequency earthquake that have been detected originate from one of these black dots on the map. Slide 4. Another particularity of low-frequency earthquake is they tend to happen in bursts. So here we can see the number of LFEs recorded per day as a function of time during a period of about 2 years. And we can see that there are days with many low-frequency earthquakes, but for many days there is little to no activity detected on the low-frequency earthquake. Slide 5. So what we usually do with our low-frequency earthquake is we download seismic data for a given period of time. We analyze this seismic data using a signal processing method and find the time of occurrence of low-frequency earthquake. With that, we create a catalog of low-frequency earthquake for this given period of time, and we publish the catalog in some scientific journal, and that's it. We leave the catalog as it was when it was published. Slide 6. But actually, seismic stations are still recording as I am speaking, and probably low-frequency earthquakes are occurring and are recorded by this seismic station. So what would be very interesting to have is to analyze the seismic data as soon as they are produced to find a new low-frequency earthquake and update our catalog on a daily basis with this new low-frequency earthquake that are just happening over and over again. So the aim of the Incubator project is to create a tool that will do just like that, download the seismic data from 2 days before, analyze the seismic data and find a new low-frequency earthquake family, and update the low-frequency earthquake catalog with these new earthquakes. Slide 7. The first thing we've done for this Incubator project is create a Python package that is going to do that. Previously, we had some Python scripts that were used to download data and find low-frequency earthquake, but they were not as well organized. So now we have a GitHub repository, which is organized with one directory with all the scripts that are necessary to download the seismic data and analyze them. There is also a directory with tests to make sure that every time we update the repository, all the scripts are still working. There is a directory with examples when we have stored all the data necessary to do the seismic analysis. So we have a list of low-frequency earthquake families and seismic stations. This is where we store the instrument response. And to look for new low-frequency earthquake, what we use is each time you have a low-frequency earthquake that is happening for a specific LFE family on a specific patch on the plate interface, the seismic waveform that is produced in the seismic recordings is always the same. So what we store in this template is what the seismic waveform look like. Finally, we have a directory which is called workflows, and I will be speaking of that more in detail after. We also have set up an Anaconda environment for the Python package. And to manage our package, we use a Python tool that is called Poetry. And with that, we have a specific file that defines our project, which is called pyproject.toml. Slide 8. Another thing we have done is previously to run the analysis, we just launch Python. We import some function from modules we have written to do the seismic analysis, and we launch these functions with some arguments. We've created command lines that will help us to run the same analysis, but just launching a command line on a bash shell instead of having to launch Python. Slide 9. This is the most important thing is we have set up a GitHub workflow which actually runs the code every day to do the downloading of seismic data and analyze the data to find the low frequency earthquake. So this is a specific thing that you can do on GitHub. You can specify different jobs that can be run whenever you want. So you can specify, for example, test jobs that will be run every time you update your repository, or you can specify as here an analysis that you want to run on a regular basis. Slide 10. So what this job actually do is first we specified that we want to run that daily at midnight. Then the script looks at what day it is today, and it looks at what day it was 3 days ago. You specify which environment GitHub must use to run your Python scripts. It installs the latest version of the Python package to run the analysis. Slide 11. And finally, we wrote a script that does the downloading data and finding the low frequency earthquake. And we run this script called Quantscript.sh. And the last part is the script will produce output files, and we want to keep this output file and store them somewhere. So we upload it and we will save it on a Google Drive. Slide 12. Another thing we did when we created this Python package is improving the memory space and the computing time. When you analyze seismic data, you do need to do some pre-processing, and you need to know how the seismic station behaves. So you have an instrument response file, and before we were storing this instrument response into the GitHub repository, but it can take some place. So what we do now is before analyzing the seismic data, we download the instrument response, we do the analysis, and when we are done with the analysis, we just delete the instrument response and it saves memory space. Another thing to do is the computing time. So a given seismic station can detect earthquake for different low frequency earthquake families. So what we were doing before is we had a loop on low frequency earthquake families and then a loop on seismic station. And with this setup, you could download several times the same seismic data from the same seismic station for different low frequency earthquake families. So we changed that, and now there is a loop on seismic station that downloads all the seismic data and save them somewhere. And then there is a loop on low frequency earthquake family when you analyze the seismic data, and you don't need to download them as they're already stored. And at the end, we delete the seismic data. Slide 13. Finally, an important thing is saving the results from the analysis. So the workflow on GitHub will produce an output file. So when we see on GitHub on action, our workflow is called cronjob, and it will produce what we call an artifact. And these artifacts actually contain the output file where the catalog of low frequency earthquake is saved. So every day it produces a new artifact with a new file. What we do is we upload it and we save it on a Google Drive that we created for this project. So we can see that for every day there is a CSV file that is created and stored on the Google Drive, and it corresponds to the low frequency earthquakes that were recorded for one day for a specific low frequency earthquake family. Slide 14. There are several improvements that we want to do on the project. The first thing is the computing time. Currently, our code is sequential, and we think that we could save also some computing time by parallelize the Python scripts. Another concern is the volume of data. Currently, it is just an example, so we just analyzing seismic data for 2 low frequency earthquake families, and it runs on GitHub in 35 minutes. But in the future, we would like to do analysis of more seismic data, and so we are concerned about possible time limit on the computing time of the job we can run on GitHub. So in that case, we're thinking about moving to Amazon Lambda instead of doing the analysis on GitHub. Slide 15. So I thank you for your attention, and I will try to answer some questions on Zoom.